Welcome to the lecture series on GPU architectures and programming. So, today we will be moving over to a new topic which is some other kinds of optimizations. Primarily the optimizations we will be discussing are fusion or fusing multiple kernels and coarsening of threads in kernels. So, they are popularly known as fusion and thread coarsening as two possible optimization techniques. So, coming to this topic on kernel fusion and thread and block coarsening. So, this will actually require you to do a small recap of the following topics like how to do a multi-dimensional mapping of data space, the concept of synchronization of threads, concept of warp scheduling and divergence, and also how memory accesses get coalesced across different threads inside a warp, and the concept of tiling and also we will see that the primary workloads we will be talking about here would be like matrix multiplication, convolution, which are the workloads on which we may be focusing a bit like that. So, getting into this topic of fusion, let's just do a recap of what is classical loop fusion. So, this is essentially a classical compiler optimization which helps to improve performance of a program. The primary reason for the performance benefit is that if I do a loop fusion operation, it may be possible to reduce the off-chip memory traffic. Essentially, you reduce the number of accesses and you can reduce the cache miss. You can also obtain better control on multiple instructions, and also it helps in reducing the number of branch condition checks that are required, and we will see that why that is so. We will just revisit this idea of loop fusion in this case. So, the way fusion of loops work is that you have two independent loops. You fuse the iterations of these different loops, and it helps in case the iterations are such that they are referencing the same data element. So, if we look at this kind of an example, so here we are just trying to give an example of loop fusion. We are not saying that in this case I will obtain a usefulness which is exactly that we are referring the same data element or not, but let us see what is the advantage we get. So, this is a simple loop fusion example. We have two loops here. As you can see, in the first loop I iterate 0 to 3, I iterate in a total of 300 times. Again in the second loop I again iterate in a total of 300 times, while in each iteration of the loops I am accessing the array elements of AI or BI. So, alternately I can fuse the loops and I can perform these updates of AI and BI together inside a single loop, right. So, what is the good thing about this fusion here? If you check the original code which was before fusion, here we are having the condition checks in the first for loop as well as the condition checks separately in the second for loop, that gets avoided, right. So, that is the advantage which we are leveraging in this case. Maybe in case of other examples which we will soon see, that suppose I have two loops which are effectively in the same iteration, they are effectively referencing the same data, then it does not make sense to do that in separate loops, and we can just bring those computations inside the same loop provided there are no dependencies, and the main thing that holds is in the same iteration, same value of I am accessing the same data AI and maybe AI minus 1, stuff like that in the two loops, right, and that is what we fuse, and we get an advantage with respect to cache access, which is fairly understood. Now, coming to our specific topic of fusion when we are talking about GPU kernels. So, again before getting into this, I will just like to tell you, this is just a very simple representative example. It does not highlight all the advantages of loop fusion, it highlights a few, but you can do a study of compiler literature or program optimization literature which is classical and find there are a lot of advantages that loop fusion actually brings into play. Okay. In today's lecture, we will primarily be studying this idea of loop fusion from the perspective of GPU kernels. We will study that how the fusions can be done, what are the different possible ways to do the fusions. I mean, in terms of handling the fusion at the thread level or the block level, and we will talk about architectural implications and other things in detail later on. So, kernel fusion is basically the kind of fusion where we are going to group a set of GPU kernels together and rewrite a single kernel. And the idea of using this is that if I fuse multiple kernels together, it may potentially increase the efficiency by decreasing execution time, power consumption, etc. Now, why is this advantageous? Let us first discuss certain issues that we have with GPU kernels. For example, whenever I am launching a GPU kernel after setting up suitable launch parameters, I have no control on how the different threads get scheduled, right? It's all it's all decided by the hardware scheduler. So, I have no control on how the threads get scheduled, and typically when one kernel is running, I won't have the flexibility of launching another kernel as long as the kernel 1 which was running doesn't finish. In modern days, NVIDIA and others support some concepts called concurrent kernel execution, through which I can launch multiple kernels together. But still, I would say that we are not having absolute control of how the different kernel threads belonging to different GPU kernels get scheduled once launched in the device, right? Now, this is something on which you can have finer control if you perform a static optimization like kernel fusion on the input kernels. So, what can be done is inside a kernel fusion operation, I can rearrange and schedule multiple kernels from the host side, right? That I will be able to control that which threads in which kernel execute first, for which threads in which kernel later on, like that, if I fuse them following some suitable semantics. So, this is something we like to see, that how such fusion of kernels can be done. Also, the other idea would be that if I am using kernels with same or different data arrays, they can be replaced with a single kernel call. That's the fundamental thing. Instead of having multiple kernel launches, I am going to launch one kernel if I am fusing multiple kernels together. And we will first study what are the advantages out of fusing multiple kernels together and writing a fused kernel. It may happen that in case I have data reuse using on-chip memory, if that is a property of the individual kernels, that they actually are accessing data from the same memory, from the same data elements, then by fusing them, I am able to leverage the reuse of the data through the hierarchy of cache and shared memory, on primarily cache, as is that's the on-chip memory, through the and also the shared memory which is there in the SM through the through the memory hierarchy of the GPU, and that would improve the performance, right? Now, of course, as a side effect, what happens is that if I am making better use of the on-chip memory, I reduce the off-chip data traffic, and that is going to provide me essentially that's what we mean by reducing the global memory data transfers. The number of data transfers from the global memory will reduce, and that reduces the kernel launch overhead, right? Because instead of launching multiple kernels, as we have repeated, that I am launching less number of kernels, because each time when you are launching a kernel, you have to set up launch parameters, you have to set up the GPU system, runtime system of CUDA will set up internally suitable data structures, and that also consumes space and time. So, that is the kernel launch overhead, which you can bypass if you are launching a single kernel by fusing two or more number of individual kernels, which the original programmer may have written, right? Now, the other advantage that may happen is you can utilize maximum threads in the GPU. That means, suppose you are launching single kernels at a time, right, and each of the kernels are not completely occupying all the SPs in the GPU, then you are not really using the full parallelism offered by the GPU. Instead, you can perform suitable fusion and utilize maximum threads in the GPU. Now, what are the limitations? Now, this kernel fusion may or may not result in performance improvement, right. So, when does it not result in performance improvement? For example, let us also understand that architectural resources like the capacity of on-chip memory and the registers inside each of the SMs, they are limited in number, right. If I fuse kernels, then essentially each kernel would place a higher requirement of on-chip memory and registers, right. That is good, that doesn't hurt our performance as long as I have enough on-chip memory and registers to support the execution of a fused kernel. But in case the requirement becomes too high, then the fusion is not really advantageous, and it may lead to further overheads and a reduction in speed up, right. Now, again in a similar way, I will have all the other points. For example, this idea that I would get reduction in off-chip memory traffic, that is also feasible up to a certain limit, beyond which that advantage will also go. That advantage will also be lost. And the other thing is, when you are fusing kernels, there may be an overhead in case the kernels do not have an identical data access patterns. There may be overheads in terms of fusing the kernels. These are the few things which we will also study. Also, in general, it may be difficult to search for optimal rearrangement of fusible kernels. So, essentially, first thing is I have to identify which are the kernels which can be fused to our advantages. Then the next problem can be that what should be the, if there are many kernels which I am deciding to fuse, and the next problem is more related to scheduling of the kernels, that can there be a suitable arrangement of the threads which gives me the best possible fusion. Now, that can also be a decision which may be quite complex in general. Let us not get to that. And also in certain cases, if I am in the process of doing the fusion, I am incorporating too many conditionals inside the fused kernel code, and it becomes way complex. That may also introduce divergence, which was not the case earlier, right. So, we have to understand that essentially this is an optimization where we are trying to exploit the entire parallelism, the entire compute and memory bandwidth available with the GPU with respect to doing the fusion. But if we overdo it, it can actually create some issues, and the speed up gains may not happen. So, one has to decide on doing the kernel fusion based on his architectural knowledge and the usability of the GPU's parallelism. So, what we will do is we will provide some examples, and we will classify this idea of kernel fusion into several formal classes and figure out in which cases which kind of fusion is advantageous. In this figure, we are just providing a basic simple example of kernel fusion. So, we are just trying to show that in the global memory we have some data segments labeled with B and A. So, let us consider that it is a big data chunk sitting in B and also similarly in A, and we are considering two kernels K1 and K2. So, this is more like a task graph, right. So, K1 is a kernel task graph, or I would say it is a DAG, right, representing the partial order relationships between the operators and the operand. The kernels are the operators. So, K1 and K2 are the kernels which are the operators, they are operating on the data operands. Like in this case, K1 is a kernel, an operator, which is going to perform a sin A plus cos B transformation on data inputs from B and A, right. So, these are the buffers containing the data, sequential data B and sequential set of data, essentially a large buffer or containing the data in A. K1 will launch multiple threads in parallel, and for each data item in B and A, it will simply compute a sin A plus cos B, right. And this sequence of values K1 is going to write in an output buffer C, right. So, this entire dependency is highlighted here in the form of a task graph. So, you have let us just define the task graph here. You have operand 1, you have operand 2, you have a kernel operation, and here you have the output buffer. These are the input buffers, right. So, I have this K1 which is following this kind of a structure, and then similarly I have K2 which is working on A and providing me as an output a buffer D containing the sequence of log A values, right, all the components of A, and in that way in the global memory once K1 and K2 have executed, we are saying that we will have two output buffers C and D filled with the outputs of K1 and K2, and then I want to execute K3 which is essentially going to take in the contents of C and D and is going to perform a further complex operation, is going to do a square root of C and multiply by D and output that in the global memory. So, C, let us say C is containing the values like that, and this is containing the values like that. So, here so, this is what you get in the output buffer, a sequence of this kind of values after K3 executes. So, this is like a task graph. We are trying to show that we have kernels K1 and K2 processing input data buffers B and A and producing the output in the global memory output buffer, right. This is the situation when we are doing an unfused execution. What happens when I fuse these kernels? So, essentially we can replace these three independent kernels K1, K2 and K3 and create one kernel called Kf. So, then what would happen is Kf would be a single kernel whose inputs would be the global memory buffers B and A. So, it will copy data from B and A, it will compute sin A plus cos B and log A, and it would have the log A in the local memory, and this is just one possible implementation. It would be storing the sin A plus cos B data elements in the shared memory. This again I am just saying this is an example, and then it will perform all the operations of K3 on these data points and then do the global write. Okay. So, this is the code snippet I have for kernel 1. As you can see that you first find out what is the total number of blocks by this statement, total number of threads by this statement. Then you use this total number of blocks and total number of threads to create I, which would be the total exactly the total number of threads that have been launched, right. So, I hope this is clear. So, I am finding out what is the block number, right. Sorry, let me just repeat this part. So, block number. So, essentially what you are doing is we are multiplying this block ID Z with grid dimension and x and y, right. So, and then you are doing an addition with block ID x dot y times the grid dimension in x direction, and then you are adding block ID x. So, in an effect all you are doing is you are considering for per thread what is the corresponding block, right. If I just linearize the total set of blocks, then what is the block in which it belongs, and then I am finding out what is the thread number for it inside the corresponding block, and then if you just execute this kind of a statement, you figure out what is the global ID of the thread, essentially the relative position of the thread across the entire input data space. And of course, we require that considering that I have these two input buffers A and B, which are one dimensional arrays containing the data AIs and BIs. Of course, they can be in another setting. Fundamentally, they would all be linear, and that is the primary reason why you would like to know the global thread IDs. So, once you identify the global thread ID, you use that global thread ID to have a linearized access to A. You just access AI, you just access BI. When is that a valid access? As long as I is less than a data size, which is a variable that tells you up to what position in both the buffers A and B you are supposed to contain. I mean, they are supposed to contain valid data, right? So you compute the global thread ID, you use the global thread ID to compute the linearized position or offset inside the array A. Similarly, the location from B, right? And then you are simply doing a sin AI plus cos BI to figure out what should be Ci, right, from the with respect to the input buffers. And similarly, for I can just do it for kernel 2. I will just find out block number, thread number, and then again compute the global ID. I will just see that whether it's going to access something valid inside the data size, and then I will just consider the corresponding position in the input buffer A using a linearized access and store the data into the output buffer Di, right. So I do a code, I provide a code snippet for kernel 1, a code snippet for kernel 2, and then I also have a code snippet for kernel 3, where I am using I as the global thread ID, and using that I am doing this computation of sqrt Ci multiplied by Di and producing the result to output I. So of course, it's very simple to fuse all this sequence of instructions to a fused kernel. All we need to do is we will have a similar implementation. Compute block number, thread number, compute the global thread ID. If it is less than the data size, you just use it to compute C, you just use it to compute D, and then use C and D and apply the last operation to compute the output I value. So this is kind of an example of fusion of kernels, and as you can see that what is the advantage out of it. Now once we understand how a fused code should look like, you can see that it is just a sequence of the kernel operations that have been performed. Now what is the control I have here? I can control this sequence, right. This is important. Let us observe what is the sequence we are doing. So we are first computing C, then we are computing D, and then we are computing output, right. Now when we look at the DAG, it's not serializing K1 or K2, it's just saying that okay, you have to execute K1, you have to execute K2. Once both finish, then you have to execute K3. So both are valid execution orders here. When I am fusing the kernels, I can do since if you look at the dependency structure of K1, K2 and K3, it's something like this, which means if I just serialize, I can have K1's operations followed by K2 followed by K3, or K2's operations, considering that I have serialized them in the kernel code, and this, right. So when you look at the fused kernel, I believe the log is in K2. So what we are doing is here, if for each thread I am doing K1's operation followed by K2's operation followed by K3's operation, this is also a valid order. So if we just execute like this, the original kernels, three arrangement of 3 kernels, essentially I leave it to the system to figure out how to execute the kernels, what should be the sequence followed by each thread and all that. But when I am fusing, that sequence is set by the programmer, right. That is one possible observation here. The other observation is, let us identify what is the advantage in this case out of fusion. Well, in this case it is a big advantage, because each of the kernels are not doing that big a computation, but there is lot of global memory reads and writes, right. So K1 and K2 are reading from B and A, then they are writing back to C and D, and then K3 is reading from global memory again and writing back to the global memory, right. If I fuse K1, K2 and K3, then what happens is I have a global memory read from B and A, and I have a global memory write which is at the final output. In between I just will have I will just have shared memory and local memory writes and reads. So that would significantly increase my execution time, significantly decrease my execution time, and provide a significant speed up here, just because I have avoided lot of unnecessary global memory transactions. So in this case, the kernel fusion operation was found to be advantageous. Now, while that was a simple example, and earlier we have discussed that there are certain advantages of the fusion operation, there are also certain disadvantages of the fusion operation. The first thing we will do at this point is we will classify the different types of fusions, we will formalize this classification, different types of fusions possible among GPU kernels, and then we will speak about what are the different advantages and what are the advantages and disadvantages of each type of fusion. So, kernel fusion primarily can be classified into three types. One is inner thread fusion, the other is inner block fusion, and the third one is inter block fusion. So, maybe we will end this lecture with this introduction of this classification, and in the next lecture we will go into the detail of each of these type of fusion optimizations. Thank you for your attention.